Okay, so this is work on a model evaluation that I've been doing using short-term forecasts of the Arctic Ocean sea ice atmosphere coupled system using wintertime statistics from the MOSAiC campaign. And this is my list of collaborators who have either contributed to the analysis of the diagnostics that I'll be showing or have contributed model output. So I was really fortunate to be a member of a team that was responsible for co-located measurements of the ocean, sea ice, snow, atmosphere at 4 different sites. And so for this study, I've been using observations of the sea ice and snow, which were led by Don Perovich and his colleagues. I was also using measurements from a 30-meter tower, and 3 3-meter towers were located at the Met City, which is right next to the polar stern, the Central Observatory. And there were 3 additional sites called L sites, which were 10 to 20 kilometers away from the polar stern. And these observations were led by Matt Shoup and his colleagues. I'm also using observations that were taken on the ship. So there were radars and lidars. And these observations were led by the DOE armed scientists. So this work was initially coordinated with the YOP processes and sea ice task teams, and then formed a smaller group, which was shown on my first slide. And this is also a YOP-endorsed project. And so the goals of this project are to use observations taken during MOSAiC to improve simulations of processes that are very unique to the Arctic, such as the persistence and maintenance of mixed-phase clouds, the representation of the stable boundary layer, atmosphere-snow interactions, ocean-sea ice atmosphere coupling, and we use short-term forecasts and wintertime statistics to identify errors that are that are due to fast processes, such as coupled cloud feedbacks and surface fluxes, that can cause biases in climate model projections of Arctic climate change. So we're using 7 different forecasts for this intercomparison. There's a whole range of scales from very localized Arctic domains to Arctic-wide domains to global domains. And the different models that we're using, the first is the NOAA-PSL coupled Arctic forecast system, which is our in-house quasi-operational system. There's the ECMWF integrated forecast system, the Météo France Arpège Gelato system, the METNO Harmony Arome system, the US Navy Earth System Prediction Capability Model, the DWD ICON model, which is the German Weather Service, and the Russian Hydromet Forecast System. And the most significant things is that 5 of these are fully coupled models, atmosphere, ocean, sea ice models. And so we really want to look at this from the perspective of a coupled system. And so I'll be showing some diagnostics, starting with really basic diagnostics and building our understanding to more coupled interactions. So this is showing PDFs of the net surface long-wave fluxes. If you look at the upper figure first, the shading is the observations. And the reason why we can have a shading range here is because we have these 4 sites that are about 10 to 20 kilometers apart. And we call this a floating climate model grid box. And with that, we can estimate the subgrid variability within that grid box. And so that's what's shown with the gray shading. And so you can see there's this bimodal distribution, which is very typical of the Arctic. So we have a clear sky mode, where we have very large outgoing long-wave radiation, and a cloudy mode where the net long-wave radiation is very close to 0, because the downwelling radiation from the clouds almost compensates for the outgoing long-wave radiation. And I've divided up the model output into these 2 figures just so you can see them clearly. If you look at the upper figure, you can see there's only 2 models that can simulate this bimodal distribution. 2 of the models have a unimodal peak between the observed clear sky and cloudy peaks. And I'll show in a minute that these models are essentially missing the cloudy mode. So what this is their representation of the clear sky mode, which is showing that the surface temperatures are too cold. The lower figure shows the 3 models that are essentially missing the cloudy mode, but have a close to realistic representation of the clear sky mode. But you can also see that all 3 of these, the clear sky mode is shifted towards larger values, meaning that the temperatures are too warm. So this is showing the joint PDFs of the near-surface stratification on the x-axis, so that's a 2-meter temperature minus the skin temperature, compared to the net long-wave fluxes on the y-axis. And the upper left is showing the observation. So again, you see this bimodal distribution. So along with the, for the clear sky mode, along with the very large outgoing long-wave radiation, you're getting very stably stratified near-surface environments with a peak at about 1.5 degrees. For the cloudy mode, so along with the very small net long-wave radiation, you're getting very small net surface stratification because the near-surface environment is well mixed. And the distribution to the right and below the observation show the two models that have the bimodal distribution similar to observations. An interesting bias in these is even though the clear sky, it has a clear sky mode with the radiation similar to observations, actually the near-surface stratification is a bit too small. Another really interesting difference is if you look at the three models that don't have a cloudy mode, that's the DWD, Navy, and IFS, you do see a hint of a cloudy mode in the IFS, but they're essentially all missing the cloudy mode. An interesting thing is that two of these actually have near-surface stratification close to what was observed, even though the radiation is a little bit too warm. So this is showing the liquid and ice water path. So liquid water path on the top, ice water path on the bottom. The shading here is actually, since we only have observations at a single site, the shading is showing the max and min of the 1 minute averages over an hour period. And the models, this is just hourly output. And in the upper figure, you can see there's only one model that is able to simulate the liquid water path that was observed. Two of the models have liquid water path at these very cold temperatures, but only for very small amounts, so less than 20 grams per meter squared. And as I showed, there are actually two models that have the bimodal distribution close to observations. And so if you look at the lower figure, that's because the one model in the yellow has way too much ice. And we've seen this in reanalyses as well, that if models that produce too much ice can have a radiative signature very close to a mixed phase cloud. So this is showing the scaled sensible heat flux, which is sensible heat flux divided by wind speed relative to the near-surface stratification on the x-axis. Observations are shown in the upper left. So each black dot is an hour average from one of the four sites. The red is showing bins in half degree. And you can see if you focus on the stable stratification, so positive values, you can see that the sensible heat fluxes become negative, so downward sensible heat fluxes that increase as the stratification increases, but then plateaus and begins to decrease again until it's essentially shut off for stratifications greater than about 2.5 degrees. And that's something we've known at least since Shiba. And this is a really interesting diagnostic because the slope of this line is the effective transfer coefficient used in the parameterizations for the sensible heat fluxes, and it's clearly not a constant. So there are two things I'd like to point out in this slide. The first is there's only 2 out of these 7 models that are able to simulate this decrease, this plateauing of the sensible heat fluxes as the environment becomes more stratified, and then the fluxes become shut off. And those are the 2 on the lower right. Another really interesting thing to note is that there's only 3 of the models that can simulate very stably stratified environments. And that's the Russian model, the Slav model, the DWD, and the Navy model. And what's really interesting about that is that 2 of those models, you can see, have constant slopes, meaning they have constant transfer coefficients. And what that means is that as the model becomes more and more stably stratified, the sensible heat flux becomes larger and larger, which you would think would shut off the ability to simulate stably stratified environments. So that's something that we would like to understand better. So what we really wanted to do in this study is to try to see is that what perspective can we look at these different forecasts and understand the balance between the cloud feedbacks, the surface feedbacks, and the turbulence in a very holistic way. And so the way that we're doing that is using the surface energy balance, because in the wintertime in the Arctic, it's a very simple balance. The storage term, if you average over at least an hour, is negligible. The latent heat fluxes are very small relative to the sensible heat fluxes. So the balance is essentially the sensible heat flux plus the conductive ground fluxes plus the net long wave fluxes. And that's what's shown in this figure here. So on the x-axis, we have the conductive ground fluxes. On the y-axis, we have the sensible heat fluxes. And the colors are showing the net long-wave fluxes. So black is for cloudy, green is for thin clouds, and blue is for clear sky. The observations are shown in the upper left. And so with the red circles here, I'm just showing some of the really interesting differences between the model output and the observations. So if you look at the two models with the bimodal distribution similar to observations, that's the CAFS and the arpège models, you can see both of these are missing with those red circles. This regime of extreme occurrences of very large upward conductive ground fluxes and very large upward sensible heat fluxes. So they're missing these extremes. And you can see it's over a range of net long wave fluxes from cloudy to clear. And so that's an interesting difference that I really like to look into. Is that because they're missing some transition between clear skies and cloudy skies? Or what is that significant that this variability is missing? Another really interesting thing is the three models without the cloudy mode, the one on the far right and the IFS model. And if you just look at the large ellipse, you can see that all of them have a lot of occurrences in a regime that is not observed. It's a regime where you have very large downward conductive ground fluxes and very large sensible heat fluxes. And so the suggestion is that because there's a lack of a cloudy mode, the model is being pushed into an unrealistic regime, or it could be because the models are tuned to try to account for the fact that the cloudy mode is absent. So this is sort of a list of some of the findings of this study. I won't go through them. I just want to say I think we have a lot of work to do if we really want to simulate the Arctic system. And so I think one of the next steps could be developing a parameterization test bed. And so I've been collecting some of the parameterizations from these different models, and anyone who would like to contribute their parameterizations, please contact me. And I would like to develop this test bed using observations from the MOSAiC tower, which has observations at many different levels. And I think that would be a really nice strategy for maybe the turbulence parameterizations, but I don't think that's sufficient to really address the microphysics. So I would really love to have discussions with people about what's the next step? How do we go from model evaluation to model improvement? So thank you for your attention.
Thanks very much. Are there any questions? Yes.
Hi. In your last figure there, the conductive flux at the surface, were they calculated, were they observed from the temperature sensor within the snow and the ice, or were they calculated as a residual between net long wave and sensible? And if they are independently calculated, how was the net budget closing?
Yeah, we've been working with that. In this study, I just used the residual.
So what are the errors in the net long wave and the sensible, so that how much do we trust this cloud on the top right there? Could it be linked with error in the sensible heat flux evaluation? Or?
Yeah, that's a good idea to really take that into account. I haven't done that.
Okay,
yeah.
Good, thanks.
Thanks. Any other questions?
I just wanted to say that's very nice intercomparison. Thanks a lot.
Thank you.
Oh, one more. Perfect.
Nice talking to me. Do you have plans to look at how GCMs? I know Felix showed that where he nuts the circulation to that observed, but I think there's problems in GCMs too, right?
Yeah, that's really interesting. I mean, that's one thing we would like to get to. One reason why we're using statistics is it doesn't have to be initialized. What are the realistic regimes? So yeah, I think these diagnostics can be applied to GCMs for sure.
One last question, yeah.
A question more with the observation than with the comparison with model. Can you say something about the melt onset and how it was triggered, and what's the relative importance of the long wave down versus the short wave during this event?
Well, these were just wintertime statistics. I don't include that. There are some melt onset studies being done by people in our team that will address that question.
Okay, good.
Yes.
Thanks.
Thanks very much.